These are the contents of our video. As I already told you, linear system, then echelon form, pivot position, then solution. We'll take two examples here, and finally basic variables and free variables. Now, the first question is what a linear equation is. An equation which is in the form of ax plus by plus c equals to 0 is said to be linear when it will satisfy this condition, that is a square plus b square is not equal to 0, where a and b simultaneously can't be 0, and a, b and c are real numbers. Okay, and now x and y are variables here. We can change the values of x and y. The values of x and y are not fixed here. Now, linear equation. You can see this equation. This is the equation of a line in 2D plane where x and y are the variables. In the same way, this is the equation in 3D plane where we have x, y and z, right? We can write this equation in this form, that is, instead of x we'll write x1 and instead of y we'll write x2, which can be written in this form also. In the same way, we'll write this equation as 6x1 minus 3x2 plus 4x3. Instead of z, we are just placing x3 here, right? Now, we are having three variables, right? Three variables and one equation here. Here we have two variables and one equation. Now, the definition states that an equation in n variables, which is x1, x2 and x1, is an equation of the form a1 x1, a2 x2 up to a and xn equals to b, where b is some constant. And yeah, it's written here. Here a1, a2 up to an are the scalars and the coefficient of the equation. Coefficient means coefficient of xi's, where I lies from 1, 2 up to n, right? Now, a general linear system, instead of taking one equation, we are taking n equation. For example, this equation is first one, b2 represents the whole equation is equals to b2, it represented the second equation, and finally am1 x1 up to xn equals to bm, it represents the mth equation. Now you can see there are n unknowns, that is x1, x2 and x up to xn. There are n unknowns and m equations, b1, b2 up to bm. There are m equations, right? After that, the next question is what when we call the system to be linear. Firstly, when we call the set of the equations to be a system, when we collect the equations in one set, it calls as system of equation. And if all this equation in that system are linear, then that system is called linear system. And solution to that linear system, the solution must satisfy each, and if we have one solution for that linear equation, it should satisfy each and every equation in that system. This is a final solution, right? Now, you can see one example here. Here we have, this is a linear system which is set of two equations. Okay, now this represented by the blue line and other equation represented by the red line. Okay, now you can see there's a point of intersection is the solution of the system. Why? Because a solution to the linear system of n equation is an ordered list of n numbers, which is x1, x2 up to xn, such that the left hand side of each equation equal to the right hand side of that equation. What does it mean? See, this point will satisfy these two equations, this one and this one, because it lies on that particular line, right? If it satisfy both the equations in that linear system, it means what? It means it's the solution of that linear system. And it means what? We are interested in finding the point of intersection to find the solution. Now, Other example you can see here. We plot these two lines, the first one and second one, which is represented by the blue one and orange one respectively. And what we did here is we saw the point, there are no point of intersection for these linear system. There is no point of intersection between these two lines. So it means that it doesn't have any solution. It doesn't intersect at any point. There is no common point of intersection. And in the same way, for this one, as I already told you, there is one point of intersection. There is one point which satisfies these two equations. It means for this linear system, we have one point act as a solution for this system. And in the same way, for the third case, we plotted the lines, first one and second one, which is the same line. Then you can see there are infinitely many points of intersection for these two equations. And what does it mean? If there are infinitely many points of intersection, it means there are infinitely many solutions for this particular linear system, right? We'll go further. Now, how many solutions can a linear system have? The solution can be no solution, exactly one solution, or infinitely many solutions, right? Now, when we call the system to be consistent or inconsistent, a linear system is said to be consistent if it has at least one solution. If it has at least one solution, what does it mean? Means if the solution is exactly one or infinitely many, then this case comes in a consistent case. And if there is no solution, this comes in the inconsistent one. Okay. Now, matrix notation. Now you can see a matrix in front of you. Now we just change this system of linear equation into a matrix. How we'll do it? We'll just take the coefficient of xi's, x1, x2 and x3. We'll put these coefficients in this matrix, which is coefficient matrix. For example, you can see here, the coefficient of x1 is 1 here, coefficient of x2 is -2, coefficient of x3 is 1. After putting the coefficients this side, we got this matrix, which is coefficient matrix. And we'll put the coefficient matrix here and the bi's, which is b1, b2 and b3 in this line. Coefficient matrix and additional bi's, and it forms augmented matrix. Okay. Now the next question is, what are elementary row operations? We'll use these row operations in the further questions you will see later. Now, firstly, there are three types of row operation. The first type is replacement. Well, it can replace one row by the sum of itself and a multiple of other row. For example, if we have 4 rows, we can change it as R1 changes to R1 plus 4 times of R2. Interchange. Next thing is interchange, which is R2 changes to R1. Okay. And finally the scaling. If we have a row R1, then we can change it to R1 into 4 times, equals to 4 times of R1. Now, what is an Euclidean form? In Euclidean form, the first condition should be all non-zero rows are above the rows of any zeros. For example, it means what? It means if you have rows of the zeros, it should lie below the rows of all non-zeros. Secondly, each leading entry in a row is in a column to the right of the leading entry of the row above it. It means if you have a leading entry here, then the next leading entry will be in the next row and in the next column, right? And next one, all entries in a column below a leading entries are 0. If you find the leading entry, then you should make all the elements below that leading entry to be 0. This is a third property. We should make this property, and finally, after doing all the row operation, all the elementary row operation, we'll get the final reduced matrix in the echelon form. For example, let's consider one matrix here, this one, and now you can see I'm choosing this one as leading entry. You can even choose 4 or 6, but it's 1 here, and I want to be much simpler. Okay, then I'm just taking the first element as leading entry. Now I just wanted to make this as 0 for satisfying the conditions of the echelon form. Then I did R2 minus 4 times of R1, which further equals to 456 minus 4 times of this, which is written as 0, minus 3 and minus 6, right? In the same way, we'll make this one as 0 because the elements below the leading entry should be 0 in the echelon form. So we are interested in making 6 to 0. So the next operation is R3 minus 6 times of R1, which is 1. It becomes 0 here. You can see the subtraction 6 minus 6 and 7 minus 12 minus 5 and 8 minus 18 is minus 10. And after doing this, we'll see the next step. You can see there are zeros in the below the leading entry 1. Now we'll go to the next column and to the row which is below the first one. We'll go to the second row and second column. Now we'll find the leading entry again. And in this case, we are dividing R2 by 3 and R3 by minus 5. It equals to 1, 2 and 1, 2. Now again, we are taking 1 as leading entry, 1 as leading entry, and again we are making it as 0. So what we're going to do is, we'll just do R3 minus R2 here because this is same. R2 and R3 rows are same. We'll just do R3 minus R2. And this is a final echelon form of that particular matrix, right? Now, you can see you reduce this matrix to a simpler form, which is this. This is row echelon form. Now, for reducing it to further, firstly, you have to make the 0 above the leading entry in that particular column. As you already know, 1 is the leading entry. We should make the zeros 2 as 0, which is above that leading entry. We had made it the 0 as 1 0 minus 1 and 1 1 2. We applied this operation R1 minus twice of R2. Okay, this is the finally reduced matrix and it called as reduced row echelon form, in which the entries below the leading entry in that column is 0 and entry below the leading entry is also 0. Okay, now what is a pivot position? Pivot position is the position of that particular leading entry. For example, if you made the echelon form in this way, in this step case manner, then you can see 1 act as the pivot column and pivot position. Pivot column is which contains the pivot position. Now here A11 is a pivot position and A22 is also a pivot position, but A33 is not pivot because there is 0 in third row and fourth row. In the same way, you can see here A12 is pivot position